Okay, so John, I'll let you take things over. Thanks for giving a talk.
Thanks very much, Colin, and thank you also to the organisers for this. Imagine it's not an easy task organising such a big meeting online with lots of different time zones and things. So thank you very much, and also thank you for giving me this opportunity to give a talk. I'd like to wish Lou a very happy 80th birthday. So I particularly remember that when I was much younger and I was learning about braids and knots, read a lot of his papers and I got a lot of inspiration from them. So thank you very much also to Lou. So the main subject of this talk, sorry, I can't seem to change. Oops, okay, sorry, don't know what happened there. So this is all joint work with, or most of it is joint work with Daciber Gonçalves from Sao Paulo. So we've been working together for quite a long time on surface braid groups and related configuration spaces. And so the idea of this talk is to give you some information about these groups. So some of the results are not that new, but some of them are newer. So I hope to give a kind of a reasonable vision about what's been going on in the area. So I have to apologize in advance that there's not going to be any knots, but there will certainly be lots of braid. So obviously interconnected, and there's some low dimensional topology as well. So the basic object that we're interested in is the configuration space of M. So here in this talk, M will be a compact connected surface without boundary, but in theory, well, at least for the basic definitions, you could take M to be any topological space. So we can see this space is defined to be the set of n tuples of M, where the coordinates are pairwise distinct. So this is a well-known object in topology. So it's called the nth configuration space of M. Some very basic properties of this space. So it can be viewed as the complement of the fat diagonal of M. And we can see this fat diagonal also as what you might call a hypersurface arrangement. So if you take M to be the plane, then, well, this thing is the classical object of known as hyperplane arrangement. So it's related to that, and a lot of work has been done on hyperplane arrangements and looking at their fundamental groups and trying to see if they're, for example, K-pi-1s. It's easy to see that this configuration space, it's an open submanifold, and the dimension is 2n, so if we take M to be a surface. And so one way of viewing this set of configurations, well, it's configurations of n non-colliding points on the surface M. So this is kind of related to, well, looking at, imagine that you might use it to study movement of non-colliding particles or non-colliding planets and such like. And a lot of work has been done also in relating these configuration spaces to robotics and motion planning and that kind of thing. So I'm not at all an expert on that, but a lot of work has been done in that area. So it's, from our point of view, the fundamental group of this configuration space is a well-known object. So it was shown by Fox and Neuwirth at the beginning of the 60s that its fundamental group is the pure braid group of M. So you could take this to be a definition, but the idea is that, well, you define the pure or the full braid group of M to be the coming from the geometric type definition of the usual braid group, except that you replace the disk or the plane by your favorite surface. And so the Pn of M here and the Bn of M here as seem to be the kind of the geometric definitions of the braid group. So well, in theory here, I should have put the word there, isomorphic, but and so this led to well, being able to also to study the Artin braid group from a topological point of view. So these two groups are known respectively as the N-string pure braid group and the N-string full braid group, if you like. So the pure braid group of M generalizes two things. So it generalizes the fundamental group. So if you take n equal to 1, then well, the configuration space F1 of M just collapses to M. And it also generalizes the usual Artin pure braid group. So if you take M to be the plane or the disk, well, then you recover the Artin pure braid group. So I forgot to say here, this is the, here you should view this space, it's the quotient space of the free action of the symmetric group on Fn of M by permuting coordinates. So at the time, well, Fadel and Neuwirth proved the following theorem. So if M is different from the two-sphere and the real projective plane, then this space is a K-pi1, so all of its higher homotopy groups are trivial. And furthermore, well, this comes as a consequence using well, topological tools, notably where you can use a theorem of P.A. Smith, for example. This fundamental group is torsion-free. So even for, I mean, the for M is, if M is different from the disk, well, I mean, people know there's lots of presentations that are known for these groups. And from an algebraic point of view, it's not, you know, it's quite difficult to show that it's torsion-free, but this comes almost for free as a consequence of this topological construction. This theorem is not true if in the other two cases, so if M is the sphere or the projective plane. And in this case, well, Fadel and van Buskirk showed that if you take the full twist braid, so viewed, the idea is that you embed a topological disk in your surface, and via this embedding, you can view the usual braid groups in some sense as being, well, I wouldn't say they're not, I mean, if M is different from these two surfaces, the embedding of a disk into the surface induces an injective homomorphism of the Artin braid groups into the surface braid groups. But in any case, you can you can construct the full twist braid that you can view as an object in your pure braid group of M. And Fadel and van Buskirk showed that well, this braid is of order 2. So the group has torsion, and so the space is not a K-pi1. So maybe say a few more words. So for a long time, Dassyberg and I have been particularly interested in the braid groups of these two surfaces. So there's a number of motivations that I'll try and explain. So I mainly stick to the case of the sphere, but it turns out the braid groups of these two surfaces are kind of, well, fairly intimately related. So if we look at the braid groups of the sphere, so one way to view them geometrically is so you're interested when you construct the braids on a geometric level, for example, the Artin braids, then you look at the plane cross the unit interval. And so if you want to do the same thing for the sphere, or you look at the sphere cross the unit interval, And well, if you look at the space between two concentric spheres, well, this is homeomorphic to the sphere cross unit interval, which is in this direction. So I should say that this figure comes from the book of Murasugi, a study of braids. So, well, this is how you can view the braids, and if you want to see them geometrically, at least in the case of the sphere. So it has a number of interesting properties. So one of the first properties is you can write down a presentation, and it turns out that the braid groups of the sphere have a similar presentation, so with the usual generators, the sigma I that we saw in previous talks, with the Artin relations. And to get the braid groups of the sphere, you just need to add one relation, which is this one in terms of the sigmas. And this corresponds to the fact that if you take the first string and you wrap it all the way around the others, and then you come back to the initial position, well, if you think of it in this diagram, in fact, you can pull this string back round on the other side of the sphere, and this becomes a trivial braid. So well, it turns out that this is it suffices to add this relation to obtain a presentation in the case of the sphere. Another interesting point is in the case of the Artin braid groups, depending on how you define the mapping class group, or the mapping class group of the disk minus, so this means minus n points relative to n points, is isomorphic to Bn. In the case of the sphere, they're not isomorphic, but there's very little difference between them. This short exact sequence, I think this appeared in papers of Joan Berman and Peter Scott at the end of the 60s. So you can, in fact, this comes from, you can view it as coming from a certain fibration, and you take the long exact sequence in homotopy, and you end up with this short exact sequence. This, as you can see, this Z2 here, in fact, this corresponds to what we said earlier, that this corresponds to the full twist braid, which is of order 2 in this group. Fadel and Van Buskirk also studied the torsion, so the elements of finite order. They showed that the group Bn of S2 has elements of these orders, or obviously their divisors, and you can view these the kind of the basic elements. So if you want to construct an element of this order, then the idea, at least geometrically, is to put n minus I points of your endpoints equally spaced on the equator. And then you put I points at the pole. So if I is 0, well, there's no points. If I is 1, you put the remaining point at the pole. And if I is 2, you put the remaining 2 points, 1 at each pole. And then you carry out rotations of this, like say for the inner sphere. And so if you do a rotation of angle 2 pi over n minus I, well, it turns out that this gives you an element of order 2 times n minus I. So when you've done a complete rotation as a homeomorphism, it's just the identity. But as a braid, you've done a full twist. And so you're not quite at the identity. You need to do the full twist twice to get the identity braid. Another interesting thing, so this was work that we did with Dasibag quite a long time ago, is that we classified the finite subgroups of the braid groups of the sphere up to isomorphism, and it turns out that the exact groups you obtain depend on n, but basically the finite subgroups are those of SU2. So there's either cyclic groups, dicyclic, or they can also be binary polyhedral. So these can be viewed. One way of kind of seeing this is the finite subgroups of this mapping class group. So the sphere relative to n points. Well, they're the finite subgroups of SO3. So it also depends on n. And then, well, you have the usual kind of covering of SU2 onto SO3, which is a double covering. And so you obtain the finite subgroups of this group by pulling back the finite subgroups of this group. So it was known that, well, the initial for small values of n, these braid groups are finite. And then for n equal to 4 and onwards, well, they become infinite. And B4 is a particularly interesting group. So it can be shown that this is a semi-direct product. So this is a quaternion group of order 8, and this is a free group of order 2. So one interesting fact is that this group has a finite normal subgroup, which is this Q8. And it can also, the same group can also be viewed in a different way. So this is the generalized quaternion group of order 16. This is the binary tetrahedral group of order 24. And so if you take the amalgamated product of these two groups over a copy of the Q8, the quaternion group of order 8, well, it turns out that this is isomorphic to our B4. So this B4 is an example, but it's a very interesting example. So there are one other interesting aspect is, well, which is going to kind of be the aim of what's going to follow. So another interesting property of braid groups, surface braid groups, is that there are relations between them, and also between them and the homotopy groups of spheres. So this slide is not directly related to the rest of the talk, but it's just to kind of give some kind of other motivation for studying surface braid groups. So the first relation between surface braid groups and homotopy groups of spheres was discovered by Beric, Fred Cohen, Wong, and Wu. So during the noughties. So they showed that there was an exact sequence of groups. So here is obviously the homotopy groups of the spheres. And these are the Brownian groups. So the Brownian braid groups for the different, either for the sphere, and here this is the disk, the 2 disk. And so we'll recall that a Brownian braid is said to be Brownian if, when you remove any string, it becomes the trivial braid. So this, if you're a lot of experts in knot theory, and so a lot of people have studied Brownian links, for example. And so, well, this is kind of the analog for braids. And so, well, they came up with this exact sequence is not short. And so this is kind of quite surprising to find a relationship between these kind of groups and then the homotopy groups of the sphere. So one way to interpret, well, kind of informally, this exact sequence is, well, if you want to find out something about elements of this homotopy group, well, you should look for braids that, in some sense, Brownian viewed as elements of the braid groups of S2, but not Brownian as braid groups of the disk or of the Artin braid groups. So in some sense, the difference of these two groups is measured by this group. So with Oscar Ocampo, who was mentioned yesterday, we proved the generalization of this result. So it turns out that, well, we have the same kind of result, but it's true for any surface. So any orientable surface without boundary. There are some restrictions on the value of n. So we need n to be at least 3 and 4 or 5 if we look at the projective plane or the sphere. So if you look at the case of the sphere, then, well, we recover the theorem 2 as a kind of well, it's kind of corollary, you might say. So the idea to proving these two results, like I said, it's not really the main subject of the talk, is to use the fact, so this was what Berwick and Cohen et al. Studied, is that so that they looked at the forgetful maps. So when you look at a pure braid, where you can forget one of its strings, so that gives you a homomorphism into from Pn into Pn minus 1. And so if you look at the set of all the kind of forgetful maps, one for each string, then you obtain a kind of simplicial structure. So you obtain what's called a delta group. And then quite a lot is known about delta groups and their relations, various relations with homotopy groups of spheres. So this is kind of just to give a few words about. So the Brownian, the idea is that if you want to find a Brownian braid, then you're looking for braids for which when you forget any string, when it becomes a trivial braid. And so one way to look at this, the Brownian braids, is to view it as the intersection of the kernels of the forgetful maps. And so yeah, there's a lot of kind of theory about these delta groups and such like. So the second relation between the braid groups and homotopy groups of spheres. So it applies to this case where when the configuration spaces are not k-pi1s. So we've proved, well, part of the following theorem. So if you look at so this is the universal cover of the configuration space. We take M to be either the two-sphere or the projective plane. Well, it turns out that this space, so this means it has the same homotopy type, or its homotopy equivalent, either to S2 or to S3. So most cases it's S3, and there are a small number of cases where it's S2. And so the idea is, well, if you want to study the homotopy groups of the two-sphere or the three-sphere, most of which coincide, this is obviously a long-standing and interesting and difficult problem. You might say, well, perhaps if we're very optimistic, we might be able to use the configuration spaces to study them. So I'm not saying that there's nothing kind of concrete, but maybe it's a possibility, and it gives a good motivation for studying these spaces. So one strategy to kind of, if we want to kind of relate these groups, these spaces and these spaces and these groups, might be to say, well, we could try and look for fibrations involving this configuration space, and then take the long exact sequence in homotopy and see what we find. So this idea is kind of motivated by very classical results. So this comes from the 1960s. So this is what's called the Fadel with fibration. So we already kind of mentioned this in passing, but on the level of braids. So there's a natural map from the configuration space with endpoints onto that with n-1 points, where all you do is forget the last coordinate. So Fadel and Neuwirth proved that this is a locally trivial fibration, and the fiber can be identified with or m minus. So if you take the base point to be x1 up to xn-1 here, well, the fiber over this point is this space, is the complement of these points. And so it has a homotopy type of a bouquet of circles. So this is a k-pi1, which is a nice thing. So when you take the long exact sequence in homotopy, the higher homotopy groups of this disappear. And so a lot of the time you're just left with isomorphisms between the homotopy groups of these two spaces. So this is the long exact sequence in homotopy. And so when you do that and you use the fact that this is a kpi1, well, then you see by induction that, well, in fact, you can go down as far as you like. So the up to isomorphism, the pi I with I at least 3 doesn't depend on n. So it's just the pi I of M itself. So recall here that M is the two sphere and or the projective plane. So in general, these groups are not trivial. And then on the level of pi 2, well, the long exact sequence in homotopy gives inclusion. So they're a priori they're not isomorphisms, but you get down to the pi 2 here then. And then, well, in the case that we're interested in, the pi 2, so the pi 2 disappears. And so it means that all of the previous things here are trivial. So this is the kind of the conclusion that you get from that. So this is one fibration that has been much studied, and so Dassyberg and I and other people have done a lot of work on studying this fibration, and notably in trying to find sections depending on the surface for this map. So, well, you could try and think of other fibrations that you could use to study the kind of the problems we're interested in. So one interesting map is to look at just the kind of inclusion of the configuration space into the n-fold Cartesian product of M. So to your n tuple with pairwise distinct points, well, you just send it to the same n tuple here. And then you can look at the induced homomorphisms on the level of, so this is on the level of pi k. So well, obviously you have a whole family of such homomorphisms. So in the case where k is equal to 1, so on the level of pi 1, this homomorphism was studied at the end of the 60s and at the beginning of the 70s by Berman and Goldberg. And Goldberg proved notably that, well, it's always avoiding these two cases, that the induced, we have this induced homomorphism. So he calculated the kernel. And it turns out, well, the kernel, I mean, you can kind of see this, think about it a bit. You can see this geometrically. I see it geometrically. Obviously, you have to work a bit harder to give a proof. So it can be viewed. So you're always embedding a topological disk in M, and then that gives you a homomorphism from the braid groups of the disk into the braid groups of your surface. And so you can view Pn as being, in some sense, as being a subgroup of Pn of M. And so if you take the normal closure of Pn, then, well, it turns out this is exactly the kernel of this homomorphism. So it turns out that you don't need to obtain this particular result, you don't need to exclude these two surfaces. So for example, in the case of the sphere, it's basically trivial because this group is trivial if M is the sphere. And so the kernel is everything. And well, this is everything as well. And in the case of the projective plane, it's a little more involved. But with Dassyberg, we proved that we still have this equality, and in fact, this subgroup. So it's always it can be difficult to work with normal closures, if you want to find presentations and such like. But it turns out that this is the commutator subgroup of Pn of the projective plane. So in fact, for the projective plane, this homomorphism is basically abelianization. So that's a kind of, well, kind of known results about this inclusion and the induced homomorphisms on the pi1. So you might say, well, another interesting problem is, well, how can we view the kind of the difference between these two spaces? And in particular, when we look at their homotopy groups, can we say something about the relation between their homotopy groups? So that's that. So with Dassy-Berg, so this was for the k equal to 1. So for the higher homotopy groups, it turns out that we can characterize the induced homomorphism on this level in a fairly elementary way. So it turns out that all these homomorphisms are injective, and they're mostly diagonal. So they send. So here you get you've got an n-fold product, and it sends, the homomorphism sends an element onto, well, the kind of the n copies of the same element here. And then there's only one case where it's not diagonal, and it's a very restricted case where both k and n are equal to 2, when in fact it's anti-diagonal. So the kind of the intuitive justification for this is that, at least for it being diagonal, is that there's no, each coordinate plays the same role as the others. There's no reason to prefer one coordinate over another. So there's no reason, well, intuitively, that this homomorphism shouldn't be diagonal, because then you'd be kind of, if it weren't diagonal, then you'd be kind of changing the roles of the coordinates with respect to each other. And it's only in this anti-diagonal case where, well, you're allowed to do something else, but it's also kind of symmetric in some sense with respect to the two coordinates, the two coordinates that you have, because, well, we're in the case n equals to 2. So you might ask at this point, okay, so I'm interested in looking for fibrations, and this map is not, I mean, the kind of this inclusion here, it's not even surjective, so there's no chance of it being a fibration. But, well, we have some tools to deal with that, so I'll say something about that in a minute. So it turns out in the injectivity case, well, it's kind of very, well, it's more, in some sense, it's more than being injective. We could say more about the groups that appear. So in most cases, the two groups here are isomorphic, and this is an isomorphism. And then there's a small number of cases where, for pi2, where this group is already trivial. And so obviously it kind of gives something that's trivially injective, but well, that's the way things are. One property that we use also in a lot of and certainly in part of the proof of the proposition here, is to look at the projection. So in some ways we're looking at the projection of this onto one of its coordinates. So I'm looking at in terms of the inclusion, so without the pi k's. So if you look at these projections, then it turns out that they're the induced homomorphisms on the level of pi k are isomorphisms, and this plays a role in the proof of this proposition 6 here. Okay, so the map, so we already said, well, this map is not fibration, it's not even surjective. However, there are classical tools to, in some way, to transform it into a fibration. So this is a construction that probably most of you know about, the homotopy fiber. So I'll give you just some very rapid details about that. So if we take a pointed map between two spaces, then we can define its mapping path. So in this way, so we're looking at pairs of elements where x belongs to x, and lambda is a path in y. And then we have what we call the homotopy fiber. So it's, well, the mapping path, but with one extra restriction here. And the basic theory of these spaces says that if we look at this map from EF, so from the mapping path into Y, which doesn't depend on X here, it just sends the pair to the endpoint of the final point of lambda. Well, this is a fibration whose fiber is the homotopy fiber. And one important thing here is that, well, if you look at this projection in here, then it's a homotopy equivalence. So these two spaces have the same homotopy type, and so they have the same higher homotopy groups. Okay, so if you take the long exact sequence in homotopy of this fibration, well, you get this thing here, and up to isomorphism, we can replace by the second remark here, we can replace pi k of EF by pi k of X. And so in the case that we're particularly interested, well, we get this long exact sequence in homotopy. So the idea is, well, we hopefully know something about these spaces and also about these spaces, these groups. And so we might find out something about these groups, or conversely, if we know something about these groups, then that can give us information about these homotopy groups. And it's more in this direction that we'll be heading towards. So we'll be able to say something about this group here. That's what we will to deduce information about these groups. So there's some, if you're not familiar with this kind of thing, I mean, you can look at kind of classical references, for example, the books by Arkovitz or by Hatcher or by Whitehead. But they're quite well-known objects, I think. So the main theorem is the following. So in the two cases that we're interested in, so either M is the sphere or the projective plane, then we can say something. So the idea is to say something about the homotopy type. So this is recall that this is the homotopy fiber of our inclusion IN. So it splits as a Cartesian product. I'll say something about the notation in a minute. So here is something that's familiar. So this is the Cartesian product of the two-sphere. And this is just the loop space of that. So you can view this as being, well, the Cartesian product of n-1 copies of the loop space of S2. So that's something that's reasonably familiar. And this thing here, well, this is, it's a kind of configuration space. So if M is the sphere, then we take M to be the open 2 disk. And there's also a group here that appears. So in the case of this 2-sphere, this group is just the identity. So we'll see where this comes into play in a minute. If M is the projective plane, then we take this M, bold M, to be the open cylinder, which we call C. So you should view the open cylinder as being the 2-sphere, but with 2 antipodal points removed. So this is kind of how we view this in our situation. And in this case, we take G to be the group of order 2, which is generated by the antipodal map on C. And so to define what this space here is, well, if G acts on a space, it's a group that any group that acts on the space X freely. So we have what's called the orbit configuration space, which is denoted in this fashion. With respect to the action, so this was defined by Fred Cohen and Miguel Chicotencatl, as far as I know. So it looks very much like the usual configuration space, except that we have this condition, which is a little bit different. So this basically says that if that the orbits, so we look at the orbits of the points of the n-tuple, and we're basically saying here that the orbits of the xi are pairwise disjoint. So if G is the, like as here, if G is just the identity of the trivial group, then we recover the usual configuration space. And obviously, if G is not the identity, then you get things that are more complicated. So this is what we just said. And so if you apply this definition in the case of the theorem for RP2, then, well, the space is this. And so you want each point, each xi to be different from xj, and also the antipodal point of xj. So this gives some kind of generalization of the usual configuration spaces. So I probably won't, I mean, also for questions of time, I won't go into the detail. Maybe I'll just say a couple of brief words about the proof. So we studied this space. Whoops, sorry. So excuse me, sorry, getting ahead of myself. Yeah, so we studied this space in the case of the projective plane. So we showed that it's a k-pi1. And so, well, that's one important. So when you take the long exact sequence in homotopy, well, this is an interesting, useful property to have. And it turns out that when you look at the fundamental group of this space, it's just as for the pure braid group, the Artin pure braid group, it can be written as an iterated semi-direct product of three groups. So there's kind of like a combing operation going on. So the group is it's a bit more involved. It's in terms of braids, it's more difficult to see because at each stage you need each point of your configuration space to avoid not only the other points but also their antipodal points. But it's you can produce geometrically a presentation of this group, and it turns out this group also has a full twist, so which looks kind of like the analog of the full twist of braid here. So as consequences of the previous two results, so let me just recall what they were. So this was this inclusion, or this, what's the homomorphism induced by the inclusion IN, and the theorem that says that the homotopy fiber of IN has a homotopy type of this Cartesian product. So this gives us, well, up to isomorphism. When you take the long exact sequence in homotopy that we have here, sorry, this one here, then well, you get this, and it turns out that the sequence becomes short exact, and then well, up to isomorphism, you can identify each of these groups with something that's well known. So this is basically just you forget one copy of pi k of S2, and the kernel is pi k of S2, and so this is in these are for these values of k and n, and in the remaining values we get something a little bit different, where this is on the level of pi1 here, so this comes from the pi1 of the usual configuration space, which is the pure braid group, and so these groups are well known, and we can see what this homomorphism here is. I see, Colin, I have maybe a couple more minutes or not.
I'd say maybe 2 more minutes if you can handle that.
Okay, that's fine. So, and I wanted to show you some. Okay, so I'll skip that. So I just wanted to say something about very quickly about the idea of the proof. So, and where the direct product comes from. So, well, this is kind of again general theory. So if two maps are isotopic, then their homotopy fibers have the same homotopy type. And if a map is non-homotopic, then, well, we have the same results, C being the constant map here. But it turns out then that when you write down the definition of the homotopy fiber of the constant map, you get a direct product, a Cartesian product, where you have your space X and the loop space of Y. So this is kind of where in the statement of the theorem, where we have this kind of structure. And the other point is that, well, it's difficult to try and calculate the idea of it. The idea of the proof is to kind of modify the spaces that we have. So in general, when we apply this result, or we want to try and apply this result directly to our spaces, the map isn't null homotopic. But by modifying the spaces in the maps, we do get something that is null homotopic. And so part of the proof is to construct these spaces for which the map is non-homotopic, and then we can apply this. This result. So maybe I'll stop there. And so just like to say again, happy birthday to Lou. So thank you very much.
Great. Thank you very much, John. Let me stop the recording.